Hello all. Today we will be revisiting a problem called stock Spain problem. So let's first understand what is the problem statement or a problem definition. We are given a list which has price of stock on a consecutive days. That means I can have a list which has prices like let's say 100, 80, 70, 60 or so on. So these are the prices on respective days. So 100 is priced on day 1, 80 is priced on day 2, 70 is priced on day 3 and 60 is priced on day 4. This is the input which is given to us. Now what is the ask? The span of SI, that means SI is nothing but S of 1, S of 2, S of 3 and S of 4, where the subscript is the day. The SI of the stock's price on a given day I, that means I equals to day, is defined as the maximum number of consecutive days. This is very important. Maximum number of consecutive days just before the given day for which the price of the stock on the current day is less than or equals to its price on the given day. So the prices or the stock prices on day 1, 2, 3, 4, 5 and 6 days is given as 100, 60, 70, 65, 80 and 85. Now we have to find SI for I equals to 1, 2, 3, 4, 5 and 6. And as per the definition of SI, it is the number of days prior to this day, let's say I, where stock price of I is greater than stock price on day J, where J is less than I and greater than 0. Actually J is less than or equals to I. So for 100 there is no day prior to 100. So we will take the span of that day is equals to 1 because only that day, the actual day has the price of stock, so it will be of size 1. So S of 1 will be 1. For 60 there is no day prior to it that has value less than or equals to it. So if we see the day 2, there is no day and the consecutive day, the just before it, right, and consecutive, which has price less than 60 is there? No. The next day or the previous day has price of 100. So S of 2 will be nothing but the day on which the price was 60, that is 1. For 70, the day 3, we have a day before it and has a value of 60, that is day 2. Hence the span is, this is 1 plus 1. The span of S of 3 will be 2 because there is a day before it and the actual day on which the price is being considered. For 65, we have 60 less than 65. It is not consecutive. There is a day in between which has price higher than 65. So we cannot consider 60. Hence, there is a day which is price 60 but not consecutive. Hence, the span of 65 is again 1. So S of 4 equals to 1. The price of stock day prior to is less than 80. Yes. The day 2 days prior to it 70, it is again less. 3 days prior to it 60, again less than 80. So when we go to 100 it is greater than 80. So the stock span of day 5 will be 1, 2, 3 and 4. That is S5 is 4. It is 65, 70 and 60 which are less. Hence, and these are consecutive. Always keep in mind that these are consecutive less than 80. Span is 4. And similarly for 85, it is less, 65 is less, 70 is less and 60 is less. 100 is bigger, so the span will be 1, 2, 3, 4 and 5. So S of 6 will be, 5. Hence, we figured out S of I for I equals to 1, 2, 3, 4, 5, 6, where S of I is equals to the number of days where SP of I is greater than SP of J, greater than or equals to, actually. We didn't consider that case. If there was a stock price here as 85 again, then the span would have been S of 7 would have been 2 because it is less than and equals to, not less than. Okay, so this is the problem statement. Now we will look So this is the problem statement, a bit confusing, but when we see the solution, it is very simple, and I hope example clarified what the problem actually is. The solution. Let's come to the solution. What will be the solution of this? The best or the brute force solution will be, let's say I have a price list as 100, 60, 70, 65, 80 and 85 as per the previous example. So what I'll do, I'll take every index I and I will scan from I minus 1, j equals to I minus 1 till j is greater than equals to 0. That means I'll go from this index backward to the first index of the array and check if, say array name is A, so A of j is less than A of I, and as soon as I find the first j where A of j is greater than A of I, then I'll break and the span of I will be I minus j. So this is clear. So simplest solution will be scan through each ith element and then check for I minus 1 to 0 for the consecutive days where price is less than or equals to that of on ith day. What will be the complexity of this algorithm? It is very easy to calculate the complexity of this algorithm. For every I will be scanning I minus 1 element. So for n elements, I will be actually scanning n minus 1 element. So 1, 0, 2, 1, 3, 2, and for n minus 1, n minus 2, and for n it will be n minus 1. So these will be the scan. So it will be sum of 0 plus 1 plus 2 plus 3 to n minus 1. This is nothing but n minus 1 multiplied by n minus 2 multiplied by 2. That is nothing but O of n square. Hence the complexity of this particular solution is O of n square. Can we do better than this? First insight what we get from the previous example is that, do we need to go till the first index of the array for each I? If not, when do we stop? The answer is as and when we find a day with a higher value of the stock price. We are interested in the day closest to I where price was higher than ith day. So we are looking for a j which is less than I and price on that j is greater than price of I, where span of I is equals to j, sorry, it will be I minus j. So if we have prices of the day prior to current day in decreasing sorted order, that means I have all the prices P1, P2, P3, so on Pn minus 1 for the nth day in the sorted order. What I can do is I can compare my price on P of n to P of n minus 1. If it is P of n is greater than P of n minus 1, then I'll compare it with P of n minus 2. If P of n is again greater than P of n minus 2, I'll compare it with P of n minus 3, and so on till the time I get a j where P of n is less than P of j, and the span will be n minus j. So if we have prices of the days prior to the current day, that is nth day, in the decreasing sorted order, that means this P of 1 is greater than P of 2 is greater than P of 3, we can go on checking till we get the price higher than the current day. So this P of j is greater than P of n. Will this work? Yes. Let's take an example and see if this works. Let's say stock prices are like 100, 60, 70, 65, 80 and 85. For the day 1, stock span will be 1 because there is no prices prior to it. For S2, sort the list prior to it. That means for this particular day, we'll sort the list like this. Hence the sorted list will be 100. Now compare the price which is 60, P of n is 60 with the last price in the list. With what was the last price in the list? 100. If the last price is greater than the current day price, that is 100 equals to 100, n minus 1 equals to 100, which is greater than P of n, which is equals to 60. The span will be current day index, that is 1 minus index of the day when the price was 100, that is 0. For S3, the sorted list will be, and this sorted list is in decreasing order. So the sorted list will be 100, 60. Let's figure out what is the stock span of day 3. At 70, so the list was 100, 60. At 70, compare it with the last price of the list, which is 60. We will compare it with 60. Since 60 is less than 70, we will compare 70 with the price prior to it, that was 100. Since 100 is greater than 70, hence the span of day 3 will be index of 70, that was 2, 2 minus the index of when the price was 100, that means 2. The S of 3 will be 2. List now becomes 100, 70, 60. Remember that this is the sorted list in decreasing order. Now at 65, so the list stock price list was something like this. So we are comparing it this. At 65, 60 is less than 65, hence it will be compared with 70. 70 is greater than 65, hence the span of day 4 will be index of 65, that is 3 minus index of 70, that is 2, that is as 3 minus 2 will be 1. Hence the stock span problem of day 4 is 1. Now again sorting this list is something like this: 100, 70, 65. Now at 80, we'll compare it with 60 again, then 65, then 70, and then 100, where the comparison will stop as 100 is greater than 80. So the stock span of day 5 is index of 80, that is 4 minus index of 100, that is 0, hence the S of 4 will be 4. List now becomes something like this: 100, 80, 70, 65, and for 85 the comparison will again go till 100, and the span will be S of 6 will be 5, 0, 5. With this approach we actually increase the complexity. Sorting of n elements take at least O of n log n complexity if we use merge sort or quick sort in good way. For each index I, sorting is done for I minus 1 indices. Hence, the overall complexity has increased to this. Can we do better than this? The first idea is, like, do we need to keep all the elements into the sorted list? So at 85, we had list something like this. And at 85, we were comparing it with 60, with 65, 70, and 80. Right? In the example, we notice that even though 60 was less than 65, the span was calculated using index of 70. If the higher price is seen with the index I, we can safely remove all the prices which are less than price at I and the index less than I. So if we see the 70 and 60, the index of 60 was 1, whereas index of 70 was 2, and 70 was greater than 60. So this condition holds. We can easily remove it from the list. Now when we come to 80, the index of 70 is 2, index of 65 is 3, index of 80 is 4. Hence, we can easily remove 65 from the list, we can remove 70 from the list. Hence, the list remains only 100, 60. So this pruning of list saves us a lot of time while calculating or while sorting the list. This improves the performance. Hence, while inserting 70, we could easily remove 60, and while inserting 80, we can remove 65 and 72. With these two, we will have a sorted list in decreasing order, but in a smaller size. With all these, we know that we are interested in the last seen day first, and then days prior to it in the reverse order in which days were seen. So when we were looking at 80, we were more interested in 70 rather than 65 or 60, because we were more interested in 70. And with all these, we know that we are interested in the last seen day first, and then days prior to it in the reverse order in which they were seen. So we are interested in price of day 3 before we are interested in day price at day 2 or then 1. So we are looking at the last day first and then prior to it. Hence, this is typical example of last in, first out, that is LIFO. What is the best data structure to implement LIFO? The stack. Use of stack. Why? I clarified why it has to be used. With the first inside, we know when to pop and the push. We know that the list has to be in the decreasing order. So pop till the last seen price or the top of the stack is less than the current price. As soon as you find the top of the stack is higher price than the current price, we will stop and push our new current price onto the stack top. And the span will be the current day minus the day with the price on the top. Big insight here. Notice something, we are more interested in the day number than the price. So elements to be put onto the stock, onto the stack will be days and not the actual price. So when we are pushing onto the stack, we will push the day number on which the price was seen, not the actual price, because we will be subtracting, right? When we are taking the span, we are more interested in days rather than in the price. So the algorithm is something like this. Initialize the span of the day 0 as 1, put day 0 onto the stack. For all the days starting from the day 1, repeat the following steps. If the price of the stock on the day on the top of the stack is less than price of the current day, pop the index from the stack. If the price of the stock on the day on the top of the stack is greater than the price of the stack on the current day, calculate the span as the current day minus day on the top of the stack. Push the current day index onto the top stack. If stack becomes empty at this step, because when we are popping, it might happen that there is no day which has price higher than the current price day. So if it becomes empty, then the span is calculated here itself. That will be the current day minus 0. That will be the span. So this is the algorithm, and now we will see how to code it. So let's code the algorithm which we saw. So I already have a stack class implemented, so I'll be using it. It supports pop, push, and is empty functions. So I'll be using that directly. My main function will create a stock price list and call the function to get the stock span of each day. So let's declare the first stock price list. So this is our list which is being created, and we have added some prices into it. So day 0 has 100, stock price is 100, then day 1 has 60, 2 has 70, 65, 80 and 85. So now we'll declare another list which will be catching the result which will be returned from the function which we call. Stock span list will be catching the return value returned from the function which we call to get the stock span list for each day. We call the function get stock span with the stock price list as an argument. Let's implement the function. So it has to be a static method because it is called by a main method which is static, and it will return a list of integers, and the name of the function is get stock span. It takes the parameter as list of integers which is stock price list. Now we'll be creating a stock span list here in order to fetch all the stock span of each day and then return it back to the calling function. As I said, I have already implemented the stack with the push, pop and is empty function, so I'll be using that. So the first in the algorithm, we have to initialize the stock span list with 1 for the 0th index. So at the 0th index we have inserted value as 1, and we will initialize the stack. So, and I will initialize, or I will push the first element onto the stack, that is 0. For the starting with day 1, I will implement my algorithm in such a way that I will pop the top of the stack as and when the top of the stack has price less than the current price, and if the top of the stack has price more than current price, then I'll just calculate the span of current day and then push my current day's index onto the stack. So we will check if the stock price at the top of the stack, the day onto the top of the stack is less than the stock price of the current day, then we will just pop up that day from the stack. So we'll do as dot pop. So we'll do as dot pop, that means we are popping up the element which has lesser price than the current day price. When we have a greater than price before, we will pop out the element from the stack till the time the stack is either not empty or the stock price on the top of the stack is greater than the stock price at the current day. When we have finished doing that, we will calculate the span. So what we have done here is, while stack is not empty and the stock price on the top of the stack is less than the current day's price, we just pop out as we reach a price, either the stack is emptied or the stock price on the top of the stack is greater than the current day's price, then we will calculate the span of that particular day as I minus the top of the stack, and at the end of it we will just push as dot push the current day index onto the stack. Once we are done with all this stuff, we will return stock span list to the calling function, which will again print it. So this is how the implementation of this function works. This is very simple to implement, but a bit difficult to understand the problem. While running the program, we get this output as 112145 as we expected. Hence the program is correct. Please follow it, and please let me know if you find some mistakes into this. I'll correct them, and do subscribe to the channel to get the new problem solved. Thank you very much. Thank you very much.